Hello and good morning, everyone. My name is Maria Christina Miem. I'm the LightCon project director at Deutsches, and I would like to welcome you to the final day of our LightCon preview week. Today, with Mr. Liebers and Mr. Opitz from the German Aerospace Center, DLR, we are happy to have them, and we're looking forward to the lecture. As you might know, within this week, we would have celebrated the premiere of our new Congress Trade Fair LightCon, the first cross-material and cross-technology platform for lightweight solutions for all user industries. Unfortunately, due to the Corona crisis, we had to postpone the premiere. So with this preview week, we wanted to shorten the time a little until next year and also offer a little sneak peek, a small foretaste of what LightCon 2021 will be all about, with high quality lectures, interesting showcases in the exhibition, and not to forget a thrilling evening event here in sunny Hanover. So I hope that we could raise your interest with our webinar series and that we will meet in person next year here in Hanover. That will be great. So save the date, 23rd and 24th June 2021. And if you want to stay informed about LightCon and maybe future webinars as well, just go to our website and subscribe to our newsletter. Or if you have any question, don't hesitate to get in touch with us in person. We are looking forward to it. So for today, I hope that you will gain some interesting insights. Enjoy the webinar. Thanks to you all for being with us, and to the speakers, of course. And last but not least, I would also like to thank our founding partner for the great support in organizing this event. Thank you. So before we start, I would like to hand over to our host, Bastian Brenken from Composites United, for some final organizational remarks. Thank you.
Good morning, everyone. Good to have you as well for the last day of the LightCon. It was an exciting week, and we still have another very cool talk ahead of us today, I think. Before we start, and before I hand over the word to the gentlemen, Dr. Liebers and Mr. Opitz, I will just briefly tell you how the structure of this lecture is. It's going to take about an hour. The webinar in the first 30 minutes will be a lecture. And during that time, we ask you to keep your microphone and your camera turned off to not disturb the speakers. And after that, we have a Q&A session where you can ask your question. And for that, we will use the raise your hand functionality in Zoom, but I will explain this when we get there. Today's talk is about sensors information flow architecture and analysis. And it's tackling the topic of smart factory. And the gentleman from the German Aerospace Center will present a very, very interesting and I think successful project they've done, and with some cool technology that was developed. So I think for many of you, this is very relevant content. With that, I'd like to hand over the word to Dr. Liebers and Mr. Opitz. And ladies and gentlemen, enjoy today's webinar. Thank you.
Thank you for the nice introduction and giving us the opportunity to present our work on the LightCon preview week. My name is Nico Liebers, and I welcome you to our presentation on the way forward to a smart composite production. Well, what is that actually, a smart production? Why is everybody talking all the time about digitalization? And why do we want to collect so much data? Well, I hope after our presentation, you have a much better idea what smart production means and what are the benefits. And we have a vision that we can use the data that we collect during production to reduce all the steps needed normally between the part when it comes out of the mold and getting it into the aircraft. The vision is to do as much quality assurance as possible already during the production and knowing exactly the properties of the product. We also want to use the data to optimize the processes, reduce scrap parts, and develop completely new process technologies. My colleague, Mark Opitz, will now show you how we started the road to smart composite production. And Mark, I hand you over the presentation. The stage is yours. Yeah, thank you, Nico, for the introduction, and also from my side, hello to everyone. As you can see behind me, the plan was for today to take you into our laboratory. Due to home office during Corona, I have to choose the Zoom function instead to give you this experience we are talking today. All right, back to the topic. All of you know the potential of lightweight construction, especially of fiber composites. They can be found wherever maximum part performance and low weight are required. Therefore, carbon fiber reinforced plastics, in particular, will play a major role in the material mix of lightweight construction for tomorrow's mobility. The production process you can see here starts on the left with the raw material, fiber and resin as input, and on the right, as an output of the process, you get the finished part, whereas the material and the final shape of the part is created during the molding process. And this very important step of infusion and consolidation takes place in a closed mold inside of a press, which means there is no feedback at all. At best, parameters of the machinery or process boundary conditions are known. For instance, the mold temperature, the injection pressure, or the clamping force. So the production is mainly based on experience, whereas if we know what's going on inside, we can act accordingly. So what we had at the beginning of our work, and almost everybody who is working in this field, was a black box, as you can see on the screen. To explain this in more detail, I've brought you an example. As I explained before, we have at least two materials at the beginning. And here you can see the impregnation process of the fiber with the resin through a glass plate. In this ideal case, the component is filled evenly and completely from the left to the right. And you can see a straight flow front, which is formed, and the component is impregnated perfectly with the resin. In reality, the materials have fluctuation, which can affect the process and the component quality. So here on the right, you can see this reality. In contrast to the ideal status, the flow fronts tend to form because there is a small gap around the component, and this edge around the component, on this edge around the component, the resin flows much faster than between the fibers. And this is also called the race tracking. Also, defects in the fiber material itself represent such channels. The result of such a complex flow front can be the inclusion of dry areas, and under circumstances, these dry areas can remain in the component and finally lead to scrap. A proper process management can prevent these inclusions or lead to their dissolution. In the end, reducing scrap is possible. The intelligent mold of the future we are talking today about, in short iFeZ, is a project founded by the German government and was our approach to find a solution for all the things happen in this black box, we started with the idea to make the process step smart in terms of transparency to generate added value. So in our case, you can see the black box here on the right. In our case, the black box is an existing mold of the previous project Colibri and represents a closed mold scenario for the resin transfer molding process of an Z frame. And hundreds of these Z frames, I have one here, and hundreds of these frames are part of the fuselage to reinforce it in a circumferential direction. So the goal within iFeZ was to provide technologies for improved manufacturing processes, which mean, on one hand, determine current status of the part and process by integration of sensor systems into the mold, and on the other hand, the central acquisition of them sensor systems and machines, as well as the preparation, processing, and visualization of these expert systems in real time. A group of 8 companies you can see down there from the fields of aerospace supplier, composite production, electrical and IT engineering, as well as measurement technology were involved. Well, to connect the real world with the virtual one, you need a sensor. So our first question was, which type of sensor system or sensor is relevant and should be integrated? And for this purpose, we have conducted a survey in industrial companies and science and asked about critical component properties in the field of aviation and carbon fiber reinforced plastics. The feedback was a list of more than 50 different features, and after grouping, we had a list of 6 relevant parameters you can see here. And together with the project partners, possible sensor systems were selected or developed in our project to identify these parameters. So before the final implementation, the selected sensor systems and the sensor technology were integrated into the existing mold using a digital mockup. And with this ability of to visualize in 3D, the optimal sensor position and cable routing was found, and also interaction between every sensor was excluded, and also the basic function of the tool, the existing basic function of the tool, the heating and the sealing were ensured. In addition, the basis for the subsequent milling work on the forming tool was laid. As a result, together with the project partners, we were able to refit the existing tool, the existing mold, with the sensor technology. A total of 7 different sensor systems were implemented based on the evaluated criteria, quality criteria. And the total number of sensors in the tool was around about 80. So this is a high number and should not discourage you at this point. We simply wanted to test whether sensor system influence each other and what a resolution as well as bandwidth we actually needed. So in reality, and for the documentation of the production process and the component quality,
significantly fewer sensors are required according to the principle start small, think big. And down here on the bottom, you can see the back of the tool with the ultrasonic sensors, the thermocouples, and the cable routing. So this is the back of the future. So start small, think big. With this statement, I would like to return to my colleague, Nico Liebers, and will give him back the mouse.
Yeah, thank you, Mark. So, as Mark explained to you, we had several project partners that each developed and integrated seven different sensor types into the existing mode. And each of the previously identified quality criterion represents a separate scientific field or field of expertise for each of these sensor systems. So for this reason, it was essential to stick to a modular design, and nevertheless, no isolated solutions should have been created. So besides solving unsolved problems, a main goal of our work, especially for us as a research facility, is the transfer of knowledge. So the barriers between knowledge providers and their field of expertise and the knowledge takers should be reduced to a minimum. If possible, the knowledge takers should be able to operate the sensor system without in-depth expert knowledge. And therefore, we need the digital infrastructure, or in other words, Internet of Things and sensor technology as a tool to build bridges between the parties involved. So at the beginning of the project, most of our sensor systems had been in a stage that we call a pseudo-digitalization. So our data could have been passed paperless, but however, a USB stick or an email have been involved, and it would still have been, it was still required to do things like importing the data and reformatting, and also synchronize the data. So based on the existing infrastructure we have here, the cornerstones for real digitalization were established. The systems and the machines must be able to communicate with each other. And we wanted to integrate people into this flow of information using the suitable and available instruments. However, digitalization should not give rise to a monopoly of interpretation. So neither the machines or the humans should have an exclusive right on the data. Nevertheless, for us, the true digitization can be described by the flow of data. Not the human being is the end user, but another computer program. So the discussions how to do this, how to manage this data flow quickly led to discussions about the necessary architecture. How do we get rid of these media breaks of the USB sticks and emails? And what does the workflow for knowledge providers and knowledge takers would look like? As a result of these discussions, we have created an encapsulated machine network in which we can provide the needed software and data company-wide. That means that we can operate multiple servers on which all mission-critical services can run fail-safe through virtualization with so-called containers. For us, the development of each service includes an so-called application programming interface, API, which you might have heard here and there. So with detailed documentation of the interface functions. And APIs are a standardized network interface, network-based interface, which almost every programming language can use or provide. So this is very inclusive to so that everybody can stay in its preferred programming language. The goal of these interfaces is to build bridges of former isolated fields of expertise, as we showed before. And because the solutions should not remain lonely islands, we want to automatically collect and link relevant information and make them available to all knowledge takers. So just a quick reminder what Mark just told you. So our goal is to detect occurring defects already during production. So we showed you the example of ideal versus complex flow fronts. So we want to detect what is happening in our black box, the mold. So do we have an ideal or such a complex flow front or something completely else? And what does that mean if we have, for example, this complex flow front on the right? Will there be defects in our mold, in our component or not? Or even, will we even have a scrap part? So in order to avoid such defects, we use sensors for quality monitoring. And one example for this is an ultrasonic based process monitoring, which is in development of our institute and is one of the former isolated solutions for experts. The sensors, as you see on the top left, are attached outside of the mold. And from there, they send sound signals into the component, and the sound signals are reflected back and the sensors receive then the response. The raw signals, what you can see on the top right, then need to be processed, for example, into an amplitude curve, and finally into information about the flow front, what you can see in the animation on the left, bottom left. So, but in all of these steps, expert knowledge is required. And for example, already for the correct measurement of the raw signals, the same applies to all the next steps getting to the flow front information. So in the course of digitalization, these inputs should be automated as far as possible, or for example, stored depending on the mold. Or users should be helped, for example, with wizards in a dialogue in a user interface to get to the right settings. So taking all these steps from before to getting from a raw signal to the flow front information you want to have, and turning them into individual services, the architecture would look like something like this here. The measurement is controllable by an interface which is running on the measurement hardware itself, and then the services on the servers will acquire the raw signals from the measurement hardware and store them in databases, and other services would then analyze the data to finally get the flow front information and so on. So the intelligence is not on the measurement hardware itself, it is implemented in services on the servers. So human users now can, for example, display these measurements graphically in a dashboard you see on the right, can set parameters and control the measurement, and also can view the analyzed data with a given analysis tools. And another possibility in the middle on the bottom is to access the services directly by these API interfaces. For example, when a research assistant wants to process the data directly, he can get access the data directly by these APIs. And not to just give you the gray theory, I want to show you now in a little live demo some of these dashboards. So I switch to my browser. So here you can see the dashboard to visualize the flowfront data we acquired during our tests in during the project. So at the top you have some traffic lights showing if the resin has already arrived at the sensor position. So this is the case for all positions here. Then here in the first diagram, you see the amplitude curve of the sound signal. So if the flow front arrives, this amplitude drops drastically, and we get a very clear signal change. And on the bottom, you have another visualization of the flow front detection. And if I go back now in time of our test before the flow front arrived, so we have still the full ultrasound amplitude, and all the traffic lights are on red. And then when I go back forward again in time, you see the first flow front detection, or the flow front is detected, and then I'll go back as I showed you before. Then after the injection is completed, we see that all sensors show the flow front has arrived. And we have dashboards like these for all of the sensor systems we integrated. So like, for example, for the temperature, we measured of the mold. So here you have, for example, the heating before the injection, and then you have the injection step at a lower temperature, and after the injection, so after the ultrasound sensors would show, okay, the injection is complete, then we can heat up to the cure temperature, and then when we detect that the cure is completed, we can finally cool down the mold and demold our component. Another example I want to give you is the pressure sensor we had integrated in the mold, where you can measure the vacuum pressure and then the resin pressure during injection. And these were the dashboard examples for humans in quotes, and now I show you the so-called API to get, for example, the raw data of the ultrasonic measurements. So in the API module we use with Python, it creates directly a documentation page. If you go to the address of the service, and then you have listed all the available methods this API has implemented. And for example, if you would want to directly use the raw signals and analyze them yourselves, or connect the service to this to the raw signals, you can even try this out in this documentation page. So if I press on execute, I get the response of the raw signal, which is a very long list of numbers, and a machine would call this method like shown here. In this way, the former isolated solution of the ultrasonic sensors, which originates from a PhD thesis and was previously reserved only for experts, can now be made available and usable by others. An important part of this is that the APIs should always provide in documentation, just like I showed you before. As an example, the previously gained information at which point the flowfront arrives can now be coupled with a flowfront simulation, which you can see on the right. During the running injection, the process parameters of the simulation are constantly adapted to the current flowfront information it gets from the sensors. And so former 1D information of the sensors is hence transformed into a three-dimensional flow diagram reconstructed from this measurement data. And the current state can be evaluated as well as the prediction of the further, where the flowfront would go after this. And we can evaluate these results if any defects will occur. And finally, individual parameters or modified process steps can be derived from these results and evaluations of the simulation, and then we can try to mitigate the risk of defects. So to sum up and give you a quick overview of the benefits. So we started at the beginning of the project with an experience-based conventional process, and we had this black box, and we had to use our long year experience to design the process. We now reached with all the sensor data and the coupled simulations to a knowledge-based process. So founded on the fusion of sensor data and the analysis methods and simulations. So with that, we arrive at transparent and efficient processes and by reducing the process times. We lower the quality fluctuations and reduce the number of scrap parts. We preserve the knowledge and make it also usable for others, for non-experts. And we reduce the non-destructive inspection by shifting the quality assurance into production. Another point is the virtual certification of each individual component based on measured quality data. And to give you a little outlook or what is now possible with our results, with developed solutions of the digitized injection and cure process of our project iFeZ, we can transfer them now to, for example, the 3 large research platforms we have in our site in Stade. For example, Evo, which you can see on the left. This is a complete and highly automated RTM chain from textile cutting over preforming to injection and cure. And the data from all machines and dedicated quality sensors are collected online and stored in decentralized databases. And another database on top keeps then track of all these relations between the data and the production history the component has passed. And the second example is the research platform Baloo, which is a large research autoclave with a big number of integrated sensor systems, just like we showed you. The sensor data is then coupled also with a cure simulation and resulting in the virtual autoclave. And with the help of this virtual autoclave, the cure process is constantly evaluated and corrected. So if we reach the required cure, degree of cure, or if things like deformation is evaluated. And the last example is on the right, the platform Trophy, which is a multi-cell robot cell for automated fiber placement with online and offline process simulation, and which is used to optimize the process and dynamically distribute the task between the robots. And also a structural evaluation is performed constantly, which is based on quality sensors. For example, if defects are detected during production, so this is used to reduce scrap and also to assure the required quality of the components. So, and with that, we come to the end of our presentation, and we want to invite you to get in touch with us if you want to tackle this road to digitalization and smart composite production with us. Our systems are also mobile, so we can take we have a kind of mobile cloud with the services implemented on our servers, and we could bring them to you. And yeah, with that, I thank you for your attention, and I'm very happy to answer any questions. So thank you.